Thank you, everyone. My name is Vijay Samuel. I run architecture for the Observability platform at eBay.
And I'm Nick. I'm the engineering lead for the Observability platform.
For the next 40 or so minutes, let's talk about how to take Prometheus planet scale. This is our journey at eBay for running a massively large metrics installation. So from an agenda perspective, we look at what observability at eBay means, where our story began, how we solved the problem, some of the lessons we learned along the way, what are the things that we are thinking about next, and if time permits, let's do a few questions. Observability at eBay. Like every other company, our journey starts at instrumentation. Developers, either through the use of managed frameworks that have instrumentation libraries baked in, for example, Prometheus client or Micrometer client, or OpenTelemetry SDKs, instrument metrics, logs, traces. They onboard their application into the observability platform. We have our own, what we call Cloud Console, where you go to your application, say that, hey, I need this Prometheus endpoint to be monitored or this log file to be tailed. And what that kicks off is a bunch of control loops that place annotations on pod specs or namespaces for our collectors to be able to harvest, which is the next step. Depending on metrics, a Prometheus endpoint is scraped, events and logs. We have log files that are being tailed, and the data is being written into our observability platform. And after this, the user has the ability, depending on if it's a log, if it's a metric or a highly structured log or event, they should be able to set up either threshold-based alerts or use one of our ready-to-use anomaly detection models to be able to detect if there are any issues with the application. Or they can use our console to be able to visualize their data in the form of dashboards. So what is the scale at which we run in? At any given point in time, there are at least 1.25 million Prometheus endpoints that are being scraped. This translates roughly to 41 million time series per second that we ingest into the platform, which in turn translates roughly to 2 billion in active time series. And these time series are being queried at a rate of 8,000 queries per second to fulfill a variety of use cases that are there, whether it be detection of load balancer connection stacking or any critical KPI that's deviating, health-aware rollouts, SLOs, which our SREs use. Some of them are in the audience. And we provide 1 year worth of raw metric retention. Where did it begin? Around 2018, this was the time where cloud native in general was catching up inside of eBay. And Prometheus also was becoming extremely popular within the open source community. And we had Kubernetes clusters running inside of eBay, and there were a lot of folks who began to spin up standalone Prometheus instances. And in a DevOps model, they were managing their own monitoring needs within their own namespaces. At the same time, we had our centralized legacy platform that was there, which basically relied on a modified version of OpenTSDB. But there were several problems that were associated with it. We used custom protocols for users to be able to instrument, which means that there is some amount of tribal knowledge that needs to be built. There were DR inefficiencies, data inconsistencies. One example is that we used to run an active-active stack, which means that sometimes data might be there in one of the stacks that's not there on the other one. We had scale issues with HBase, availability challenges again with HBase, and it was a massively complex platform that we had to run, which had years of tribal knowledge baked into it. A new person to learn the platform was not a straightforward task. So what we wanted to do is build a system that was simpler and scales a lot better. It needed to be very community focused, not only in terms of ingest, but also in terms of querying as well. So standard protocols like Prometheus endpoints, and on the query side, a very rich ad hoc query language support, similar to keeping PromQL in mind. And we wanted to be able to support any application as long as it was cloud native. So deploy it in Kubernetes, add a few annotations, expose a Prometheus endpoint, and then you should be able to get monitoring out of the box without having to learn anything that is specific to eBay. So Prometheus is by far one of the more popular time series databases that are there. It's CNCF backed, offers PromQL. It's very simple to operate, given that it's a single server. It's a single server, no sharding, replication, nothing. It offers instrumentation clients in a variety of languages that are there. A very simple exposition format to be able to announce all the metrics that are being harvested. And through various techniques that have been baked into the project over several years, like delta-delta encoding, it's fairly efficient in storing time series. But there are some challenges with adopting stock Prometheus. For one, when we had to migrate from our legacy platform into the new one, we wanted the ability to be able to push metrics into the TSDBs. And at that time, there was no concept of remote write receiver, which exists right now. So from a feature parity perspective, this was something that we did not have. Federated view of data was extremely complicated, especially if you say that, okay, you have a massively large installation with hundreds of Prometheus instances. But it was very surprising to see how Cloudflare was able to pull that off. And scaling is hard. So the two ways in which you can scale is either vertically by throwing CPU and memory at the problem, or you manually shard and then run multiple Prometheus instances per Kubernetes cluster, either one per namespace, or some fancy mechanism to shard the endpoint so that you are divvying up the raw time series. So we set some initial goals while doing the replatforming, where it was first and foremost to keep it simple. So we did not want to solve things like replication. So instead, what we did is we said we'll just do fan-out writes. So if an ingester sees a time series and there are 3 replicas to write, we just replicate 3 ways at the time of ingest. If you're not able to do write into one, it's OK. It's something that we can take care at the time of querying by doing deduplication. And then we wanted to use the Prometheus TSDB as is. So just use the storage SDK to spin up the Prometheus TSDB and then write stuff into it. We wanted to do very simple tenanting. So we have the concept of what's called a namespace. And a namespace basically houses all the time series for a given application. And we wanted to be able to pin a certain application's namespace into a specific cluster of TSDB instances that we were managing. We wanted it to integrate tightly with Kubernetes. By this time, we knew that everything inside of eBay at some point in time will be fully in Kubernetes clusters. So it only made sense to be fully kube native and then say that, OK, not only for realizing the TSDB clusters through stateful sets, but also to discover which time series goes into which TSDB cluster. Just use the API server, use some CRDs to do the mapping, and then use it at the time of querying and ingest. We wanted to support PromQL and Grafana, 2 widely popular ways of observing your data that you're ingesting, and support alerting and recording. So a user should be able to roll up if their cardinality is high and they want to view the data for a longer period of time. They should be able to set up threshold-based alerts. And the initial goal was we were supporting 2 million time series per second. We should be able to get to at least 4 million. But the outcome was wildly different. So the first pass, we basically went for a centralized approach. So depending on the number of Kubernetes clusters that the metrics platform was deployed, you could have data that's coming into a well-known endpoint, ingest endpoint, which will be routed to one of those two Kubernetes clusters. And the ingest node, what it basically does is that it looks up the API server, knows what are all the replicas that it needs to write to, and then it does a fan-out write. Similarly, when there is a query that's coming in, it's the opposite. It goes into one of the query nodes in one of the Kubernetes clusters, and it figures out all the replicas that it needs to query from, query, dedupe, and then return the data. This is more from the storage and the management perspective. So we have what is called a metric store controller, which is nothing but an operator, which looks at a CRD, figures out the number of shards that a given cluster needs to have, uses that to realize stateful sets which have the actual metric store replicas. Ingest uses the API server to figure out where to write. The query uses the API server to discover where exactly the namespace is located and fires the queries. But there were challenges still with this approach, in the sense that our growth was, for many years, 100%. We started at 2, went to 4, 8, 16, 24, and now we are like 40, 41, and still rapidly growing in the amount of time series that we are accepting. The tenant-based query routing is fundamentally flawed, in the sense that the tenant information is present on a CRD, and we use that to discover which replicas we need to query from. This means that every query absolutely has to have the tenant information. Otherwise, you will have to go to every replica that's out there to figure out if it has the data and then return back. So given that the namespace is now a mandatory parameter, you cannot do things like support labels API out of the box and then fulfill Grafana on the Grafana Explorer. You cannot do autocomplete and things like that. It's still hard to support high cardinality. So you can have a TSDB cluster that's reserved for a single namespace. You can have, say, 20 shards, but still you will run into a cap where you can ingest everything, but it's very difficult to query stuff out, because the more the time series that's there with the PromQL being single-threaded and other factors is going to be very slow, or it's not going to be able to fulfill the query. And when we are monitoring, given that you're moving across Kubernetes clusters, in certain cases across regions, there's going to be a network that's involved, there's going to be a load balancer. There are so many dependencies that can fail, which prevent you from doing what is necessary, which is basically to be able to alert when something is going wrong. So at least for the cardinality, we did an incremental improvement where we introduced the concept of an aggregator. So what do aggregators do? They drop labels before the time series hits storage. And why do we do that? In many, many cases, if you look at months worth of query logs, the instance ID or the container ID are things that people don't always ask for. So why do we need to incur that cost? If no one is asking for it, might as well do a streaming aggregation to drop those labels and only write the time series that is actually going to be at a granularity that is actually going to be queried out. And this also boils down to the fact that storing raw series is extremely costly because there is a certain memory overhead for every raw series on the Prometheus head block. So when we did this, we had massive savings in the sense that we could get up to 60% CPU savings and 80% memory savings if you do it as a stream-based aggregation as compared to doing something like, okay, you use a Prometheus recording rule, roll it up, and then drop the raw series. So the savings were pretty massive on this. So to look at it pictorially, you have data coming into an ingest endpoint. Data goes into the ingester, where there is a policy, where you say that if you see this label matcher pattern, the other way around. So if you don't see a policy that can be applied, you directly write the data into the TSDB. If the policy matches, you put it through the aggregator. The aggregator knows exactly what labels to drop. it does a stream-based aggregation and then writes only the aggregated data into the TSDB. At this point, we were like, OK, let's figure out how to take things planet scale. A few years ago, there was this white paper that Google published. It was called Monarch, and they dubbed Monarch as the planet scale time series database that they run internally. And like every curious engineer, Nick and I were like, is it possible to replicate this inside of eBay? So there was an internal hack week that happened a few years ago. Nick, myself, our metrics track lead, Sandeep, Frisha, and Karthik, 5 of us, we basically sat down and we were like, OK, we're going to replicate this paper with as minimal code as possible, and we're going to do it in 5 days. And at the end of the 5th day, we had independent metric store installations running on running in different regions across the world with a single endpoint that was able to exactly figure out where to get the data from, do the aggregation, and then return it as if it was a centralized installation. So it's like, OK, theoretically, this works. How do we take it further? But this isn't as easy as one might think, because the first thing is that Google has awesome technology. And for us to be able to replicate this, we'd have to make substitutions, preferably using open source technology. And to be able to spread out the installation across various regions, spec management is critical. So the approach that we took for that was GitOps. Make sure that everything is available in Git. And you run control loops that can take the configuration to every region that you desire to. And the other challenge that was there is that the white paper is all that we had. And some of the aspects that we really wanted to know, the white paper didn't fully talk about. So at one point, it was like, we have to figure this out along the way.
So in terms of where we're going with planet scale, just kind of going over the general points before we get into more of the details. One of the primary goals that we need to achieve with this is to figure out how can we scale just storing the data better. With the centralized model that Vijay described, we still have a problem in that there's only so many resources we can consume in a given set of Kubernetes clusters to scale all the data that we're getting. And when there's more AZs and POPs and other Kubernetes clusters that are being popped up internally in our infrastructure, we start to run into resource constraints. So by trying to keep the data closer to the source, we would have effectively spread out the resource utilization across our infrastructure, as opposed to kind of trying to centralize it into a single place. A natural side effect of this, though, or the trade-off that you get, is that if you're keeping the raw data closer to the source, you're going to naturally have less availability of the data, because you're not going to be like replicating across 3 or 4 regions. You might be constrained to a single Kubernetes cluster or an availability zone, depending on how you're deploying this. But most of the time, people tend to rely a lot on rolled up data for doing like alerts or other types of visualization at particular scales. So one aspect that we did is, well, if you do a roll up, we're always going to propagate it up to another tier in a tiered storage system, which is what we are kind of migrating this to. So you have increased availability of that roll up. Another aspect of this is, if we're pushing everything out to the edge and keeping data closer to the source, we have more storage systems or deployments that we have to potentially interact with. So how do we avoid blindly querying all of them, which would be basically a non-starter from a query scaling perspective? And really the only way, and this is where the Google Monarch paper really came in for us, was they described something note of a field hint index, which kind of acts like somewhat like a Bloom filter, but it's not really a Bloom filter at the end of the day. But you can basically say, here's all this thing I want to query, give me hints on where I should potentially query the data from. So this is what we have also replicated based on the paper to kind of minimize the fan out. And then as a part of deploying this, we also have to make sure that our end users are not really aware of the fact that we're spreading the data out towards the edge. So we still need to provide a single query endpoint for them to hit so they don't have to change endpoints because they want to query something on one AZ versus the next. And then also, as Vijay mentioned, because of the sheer number of deployments that we would end up having at the end of the day compared to the centralized one, even though they would be smaller resource-wise, but there's just many more of them spread across the infrastructure, we have to be more stringent on adoption of maintaining specs in some type of source control like Git, and then relying on rollout automation to actually do deployments. So getting into an example of the deployment architecture, so we first have this notion of a leaf, which is basically the lowest tier that you would have. And in this case, it may represent like a particular Kubernetes cluster. And so that's where all the data, all the applications and infrastructure in that particular Kubernetes cluster would reside in storage in that Kubernetes cluster. So that's where ultimately we're spreading out all the resource utilization across our infrastructure. And looking at the picture, like not describing every possible component that we have, but kind of the base components that we would have in a deployment here is of course you have TSDB for storage, you have a query and an ingester interacting with it, you have a ruler that's evaluating recording rules and alerting rules, that's forwarding things to an alerter, and then there's the indexer piece, which we'll talk a bit more about later, which helps with the fan out that we mentioned. Going one level higher, this is like, as I mentioned, this is primarily for like we would store rollups in a higher tier, or there might be some use cases to where maybe the source data doesn't naturally align to something that the leaf is tied to, like a Kubernetes cluster. So it might store some raw series there as well. And in this particular case, you could think of a zone as maybe like, depending on how you want to deploy it, like maybe an availability zone or a particular geographical region. And then you also see in the zone that it has the exact same set of components that are in the leaf as well. And then within communication between the different tiers is you have basically, the things to call it is that the indexer would propagate information from the lower tier to the higher tiers for discovery purposes. And then when queries federate, they go from higher tiers to lower tiers. And then at the very top, at the highest most tier would be effectively like the root. This would be the central place that most queries would probably come in. And it's this tier alone, if you don't have anything else, is effectively what we have today with our centralized model, where it's deployed in multiple geographical regions. So the one thing that we wanted to make sure while we were doing this, and you only see 2 lines crossing any of these tier boundaries, is because we wanted to minimize the communication and dependency between the tiers, so that if there's a failure, like a critical outage in like one tier, like in the root, it doesn't cascade all the way down. So if there was like a root outage for some reason, we could still directly go talk to and issue queries to like any particular zone and still get data out. And then likewise, any like alerting or recording rules running within that zone would continue to operate even though the tier above it is having an outage for some reason. So quickly going over the ingestion overview. So the majority of our data comes in through scrapers, which happen to be open telemetry collectors at the moment. We have some push use cases, but typically this is all the data is largely going to come into the lowest level. So it could be a leaf in some cases if we have it, or maybe just a zone depending on how we're the deployment and the use cases. As I said, some of the push use cases may skip like a leaf if it exists and go directly to a zone or a root depending on the need. So some examples would be like if we have services collecting metrics for like network devices, that doesn't necessarily naturally align to something like a Kubernetes cluster level, and might apply more to like an availability zone. So it would run and then send the data straight to the zone ingestion to store the data, the raw data there. Or another example for like the root is, there might be something that's collecting business level metrics that would just naturally just align itself and store itself in the root. And in all cases when ingestion happens, there's always more than one replica that gets written to in all these cases. So on the query side, this is kind of the more difficult part of kind of switching to this decentralized model, is to kind of decide where to send queries. And it's really just dependent on the indexer information that's available. So as I mentioned, the indexer is an implementation of the field hint index described in the Google Monarch paper. Quickly, not to get into too many details, but just enough context for this talk, is that an indexer consists of fingerprints. And a fingerprint is a consistent hash of a label name and an n-gram of a label value. So by default, we produce trigram fingerprints for all labels, full string fingerprints for things like metric names, and then we can also specify custom n-grams for certain labels to provide more accuracy if needed. One example for this would be like pod. When we did some experimentation just relying on trigrams for doing a query that would have a metric name and just a pod, did not really help reduce fan out just because there's so many, there's only so many combinations of trigrams you can create for something like a label like a pod, and there tends to be tons of overlap across tens of Kubernetes clusters. So by using 4 grams, we actually got the fan out reduction we needed, which was accurate, I think, if I remember, like mostly like 90% of the time or something like that. So the way that the fingerprint propagation works is that everything first starts within TSDB. There's basically what we're doing is we are fingerprinting all of the TSDB blocks on disk. We're also fingerprinting the stuff that's actively being added to the head block, and then the indexers locally to whether it's in a leaf or a zone, depending on where the TSDB is, will discover the TSDBs. It will initiate a long-lived streaming connection to the TSDBs, and then optionally any tier below it as well, if it's a higher level tier, to receive fingerprint updates. And the indexer also, as it receives these updates, it retains a mapping of, this fingerprint was seen by, targets 1, 2, and 3. So it kind of, when we ask it later on where to send data, it basically is like a multi-map. So coming in for the query standpoint, when a query is initiated, it's typically going to come in through the root, at least going through something like Grafana where our dashboards are and stuff like that. It's going to talk to the root indexer to basically say, hey, given this expression which has these label matchers, I want you to, we're going to generate some fingerprints for that, and then go ask the indexer what targets have these fingerprints, all these fingerprints that I need. It's going to get the result of the targets that it should go to, whether it's some local TSDBs at the root or whether it's zones that it should be forwarded to. And then the query would then continue to propagate down the tiers to the zone and then also the leaf, where in each hop it would be asking the local indexer. So in this example, when it gets down to the leaf, it says, okay, well, what TSDBs here might have this data? And then after it gets that back, it would actually contact those TSDBs to get the data that it needs to evaluate the query. So kind of the last piece of the puzzle, at least from the query side, is so we have the setup to where we're going to be able to store a lot more time series, and we have use cases where their data sets for the applications that they're monitoring are getting just continuously larger and larger. But as Vijay mentioned, one of the limitations we have with PromQL at the moment is that it's evaluated by a single Go routine. It needs to see all of the data to do it, and that has inherent limitations on being able to get data out of the system and do an evaluation. So we're trying to address this with 2 things, which is query pushdown and projection. So Pushdown is what enables us to kind of take mergeable parts of a query expression and push them down to lower tiers to distribute the query execution and also limit data movement. So given this example, we have a pretty typical histogram quantile query, and there's typically always like there's going to be a sum in there. And if we look at the sum, this is something that we could completely push down as far as we can down to the tiers and have that evaluated independently, because every hop that these queries take is going to be working on an exclusive subset of data. And so they will be able to do these evaluations and then kind of roll them up, and we can merge them. So we don't, we kind of distribute the evaluation execution down as far as we can and parallelize it, and then also minimize the data movement coming back up. So in this example, we would see this particular expression come in. We say, okay, well, we're going to take the sum, and then we're going to push it down to whatever zones that the indexer told us to push it to. The zones will get it. It'll basically go through the same process. So I'm going to push it down to certain leafs that I should be querying. And as soon as it gets to the leaf, that's where the push down would stop, because now we have to interact with storage and go fetch data from storage. And then this is where projection comes in. So the other thing is, when we look at queries like this, at the end of the day, the PromQL engine or any evaluation we're doing really only cares about 2 labels. It cares about the cluster and the LE label, but we might have 25, 30, 40 labels on the time series, and if a query is involving like 500,000 series, that's a ton of resources wasted transmitting the data from storage to the query. So projection will make sure that when the leaf query gets it, it says, okay, storage, I only really want you to send me the time series that has these 2 labels on it. So we minimize that traffic as well. Then going back up the stack, the leaf query will get the data from storage. It'll basically do the sum evaluation locally, push it up to the zone. The zone will get it from 1 or more leaves. It'll kind of merge the results from those and then push it up to the root. And then the root will basically have, instead of the PromQL engine doing the sum evaluation, it will have a pre-aggregated set of time series being fed into the histogram quantile instead. So we've completely distributed the execution across wherever the data resided.
So what did we get out of this? First and foremost, we were able to get better scaling capabilities for higher cardinality. Like Nick explained in detail, like we are now able to store the raw cardinality closer to where it was harvested, which means that we don't need large installations to handle larger use cases. We can keep fanning out depending on the number of Kubernetes clusters these applications are actually deployed on. And with the help of query projection and pushdown, we can do a scatter gather in a very intelligent way and gather a minimal number of series that is required to do the actual query. So we were able to get better ingest and query performance. So one of the things that we did was keep the end user ingest and query contracts the same, but internally we had our own gRPC APIs that were purpose built, and they had some optimizations to manage symbol tables and query pushdown and projection, which greatly saved on CPU and memory utilization on many of our data paths. The metric stores themselves became independently usable. Especially the leaves, you can do short circuit monitoring that makes sense within the scope of a cluster. And a zone outage or a leaf outage can have some implications on the overall data availability, but it doesn't bring the entire system down or degrade the entire system. And because we are able to scale horizontally through the use of leaves, we no longer need to manage different TSDB clusters with different configurations based on how much cardinality a given tenant is intending to send us. So now we have fixed size TSDB shards, and it's a lot easier for us to operate at this point in time. So some of the lessons that we learned Independently usable metric stores makes life a lot easier, especially when you have like root level outages and things like that. So you can have something like a Grafana dashboard that's shipped to each and every Kubernetes cluster along with our query endpoints. So worst case, you can just view the dashboards for that cluster, and you should still be able to do operations effectively. GitOps made life very easy for us in the sense that specs are no longer managed directly on the API server. Git provides the required audit log. It's easy to roll back by just reverting to the previous table commit. And with such a massively distributed system, it wouldn't be possible for us to manage specs without the use of GitOps. Internal APIs aren't a bad thing. As I mentioned, like we reuse the Prometheus contracts on the end user front, but internally the amount of cost savings that we got was massive, more than 50% in certain flows. And it also enabled us to provide new features. So as long as the end user is not impacted by a certain thing, and we are able to absorb the complexity, it was worth biting the bullet and going down that route. Continuous observation and evolution is key. This is one of the nice lessons that we had. Sometimes like we tend to shy away from doing a certain change because it's like, okay, we're going to rewrite everything as a result. Is it worth it? Just because we took that risk and we moved away from centralized into this model, now we have the capability to scale to a great extent. The initial vision that Nick and I had when we wrote the internal memo for this one was 1 billion writes per second. Now we are at 41 million. With such an architecture, it will be possible, if necessary, for us to get to 1 billion writes. And the only way that was possible was because we did not shy away from this rewrite. What's next? As I mentioned earlier, like there are certain aspects of the user's data that they barely ever use. For example, like a pod label or a node label. How many times does a user actually ask for it? So one of the things that we have been considering is to do automatic rollups. So if every time series were put through our aggregation tier and implicitly being rolled up and then being put into the zone at a much higher granularity, you could effectively say that, okay, in a week or a month, I shed all the raw metrics because hardly anyone uses it. And the amount of disk you end up requiring for storing a year's worth of metrics or several years' worth of metrics with such a model is substantially lower. And all you need to do is to make sure that when a query comes in, the zone needs to query the right time series based on if it's available on the zone or should it push it down to the leaf and things like that. It's still not fully worked out, but this is one thing that we are considering. Support native histograms. Prometheus supports native histograms now, given that we have our own magic to do things like push down and projection, like how do these things work, how much savings we will have in terms of cardinality. So these are things that we want to figure out as time goes by. And last, like, if you think that whatever you heard in the last 30, 40 minutes is interesting and you want to try it out within your organization, let's talk. We may be open to open sourcing this entire thing. That said, any questions?